Today we'll be programming the game of life. So this is the final program we'll be creating. And without further ado, let's get started. So open up your development environment, and yeah, I'll show you the dependencies that we have first. So as you can see here, we have GLAD for loading the OpenGL functions, GLFW for the window management, and GLM for the math stuff, like concerning vectors and stuff like that. So yeah, open up a Main.cpp file and just check that you can write hello world without any problems. And once you're sure that you can do that, we can get started. So the first thing we'll need is a window, right? Without a window, we can't render anything. So we will be creating a screen window class. This class will have a public constructor, and this constructor will take a string view for the name, which are the title of the window. Then you'll also need a glmvec2 for the size, or the initial size. And we'll also go ahead and store that as fields in our class. Now, one thing I have to mention right off the bat is that we will be writing all of this in a single file. Obviously, this isn't the most modular way of doing things. However, this video isn't really intended to create the perfect program, but rather as a proof of concept. So it should give you an intuition about how you can create the game of life with OpenGL. So yeah, now that we set those fields and also store them in our class, we can go ahead and create our window. And before doing that, we need to initialize GLAD and GLFW. Well, we have to initialize GLFW first, so let's create a function for that called initialize GLFW. And yeah, in there, if we fail to initialize GLFW, we throw a std runtime error, which can say something like fail to init GLFW. Otherwise, we can set window hints. So GLFW context version major will be 4, since you're using 4.6. So the minor will be 6. Next to that, we'll use the core profile, GLFW platform. How was it called again? GLFW OpenGL profile. And in there we'll use the core one. GLFW OpenGL core profile. Okay. And yeah, that's it. So in here we'll call initialize GLFW. And we can go ahead and make this a private function of this class, since no other class will be using it. And let's also ensure that this is only initialized once. So let's create a static bool as GLFW initialized. And let's set that to false. And in here, we'll call true. We'll set it to true since we have initialized it. And if that is already initialized, we'll just return. So this can be called safely. Now we can create the GLFW window. So let's also create a field for that. window to be glw create window. For the width, we use size.x. For the height, we use size.y. For the title, we'll use title, and those two will just be mod pointers. One matching function call to glw create window. Because it takes in a const child pointer, so we can't pass in this, but rather the raw pointer. Okay, this can also fail, so let's ensure it didn't by doing this and throwing a stitch runtime error if we don't have a window. So we'll just write fail to create a glw window, and other than that we can set the context current to that window. And let's also set the window user pointer to be that window of, so to be this. Now you might ask yourself why we're doing that. We'll add a frame buffer size callback to this to the screen window. So each time we resize, a callback is called, which we'll define now, which we can call frame buffer size callback. And what we'll do in here is simple. Well, we first have to define it properly, so it takes in the glw window and window, or just window since it's not a field, and we'll add the height and the width. And in there we'll set this to be this function, right? So now each time we resize the window, this frame buffer size callback is called. And what we want to do in there is to set the size of our window so that it is up to date. So we'll set m size to the new size. So we'll define this public function that anyone can call, and then in here, since we set the user pointer, we can also get it again, and we set the user pointer to be the screen window instance. So what we can do is, so this returns a void pointer, right? But we can cast that into a screen window pointer. And let's first do this so that we can do that properly, because otherwise it would not be defined. Or we can do this and then further define it down so that we do like this. Now we can get the we can set the screen window to be this, and because we did that, we can now call screen window.setSize, and we'll create a new size with width and height. Okay, and now we'll call GL viewport. The x, so the beginning will be 0, 0, and the width will be the new size.x and new size.y. Yeah, but to call these functions like GL viewport and stuff like that, we still have to initialize GLAD, so such that the loaders are loaded of OpenGL. So what we'll do in here is, after setting the context and stuff like that, we can initialize GLAD. So let's call a function called initialize GLAD, and we'll still have to define it in here. Void initialize GLAD, and we'll do in here is we'll say if not as glad load GL loader, and then we need this GL load proc function, and GLFW provides this function called get proc address. Yeah, there it is. And if that fails, we can throw a set runtime error saying that glad failed to initialize. Yeah, but otherwise, well, glad was initialized. Let's also create a field for that called as glad initialized, which is also initially false. And if glad is initialized, we'll just return. And on the first initialization, we'll set that to true. And yeah, so we still have an error, it seems, and that is the error, yeah, obviously. So for those of you who don't know, I have a automatic include formatter, and glad has to be included before GLFW is, for there to be no error. So I have to add this no include format in my development environment. On your machine, you probably won't have to do that, but yeah. So if as glad is initialized, we'll return glad GL load as glad is initialized. Okay, nice. So this is all of the boring boilerplate we had to do. And yeah, that's pretty much it for the initialization stuff. And now we can expose like things like if the window should close through GLFW, window should close, and window, we'll return that. Or things like swapping the buffers, so the front and the back buffer, GLW, or swap buffers and window, and this will just be void and still cons because we're passing a pointer copy to this swap buffers. And yeah, let's create a main loop. So we'll create a screen window called window. The window will define the API taken the title. Let's call it game of life, and let's make it 100 by 100. This is irrelevant since I have a tiling window manager. Now, while it shouldn't close, we'll pull the events. What else will we do? Well, we'll swap the buffers as well. So let's call window swap buffers, and let's also clear the color buffer bit. And since this is two-dimensional, we won't have to add like depth buffer, but a stencil buffer, anything like that. Okay, so if we did everything correctly and compile all of this, yeah, we get an empty window. Nice, great milestone. Next thing to add is the actual rendering code. Yeah, okay, so let's add the rendering code. Okay, so since this isn't the first time I programmed this project, I'd like to explain to you the main split I did back then when I first programmed this. So basically what I did is I created a pixel manager, and I created a game of life manager. So the pixel manager exposes a public function called add pixel, where you provide an X and a Y component, and the game of life is the actual thing that is responsible for handling the game logic. So basically the game of life will be updated each iteration, and it will inject all of its state into the pixel manager by adding the pixels, and then the pixel manager will be flushed and all of the state of the game of life is rendered to the screen and removed from the pixel manager, and the game of life instance will have to inject its state each frame. So this is the basic setup I'd like to achieve in this video. So let's go ahead and do that by first creating the pixel manager class. So this we'll put up here, and let's create this pixel manager class. So the pixel manager, this pixel manager, as I said, will have a vector of vectors. So the pixel manager will handle a lot of the GL stuff, right? So it will create the vertex buffer, it will create the vertex array, it will create the shader program. All of that stuff will be handled by the pixel manager, right? And since the pixels are arranged in a contiguous sequence of bytes, if we store them in a vector, and we have to inject all of that data into the vertex buffer, using a vector is the most optimal way of doing things, since firstly, like if we were to use an array, for example, we'd have to provide a compile time size, and yeah, that would limit ourselves by doing so, because like then the game can go on infinitely. And imagine you're extending this project and trying to add something like I don't know, something like dragging. Then if you were to use an array, you couldn't drag endlessly, for example. With a vector, we have the most optimal solution, I'd say. Now what we have to do is we'll have to create like this flush function, and basically in here we'll create this pixel manager class. Okay, this pixel manager, and I'll just add this game of life class already, so that you see the bigger picture we're trying to achieve right now. So basically what I want to do is this thing right here will be updated, right? So this thing right here is the thing that manages all the game state, all the updating of the pixels and stuff like that. So we'll need an inject function which takes in a pixel manager, and it'll inject all of its data into there, and we'll expose this add pixel API, and basically the game of life will inject the data that it has. So we'll create a game of life instance in here, and each iteration will call game of life dot inject your state into the pixel manager, and then we'll call pixel manager dot flush. So that's the state that we injected into the pixel manager will be rendered to the screen. So the flush is, well, I think a better way to say this is render, or flush render. And why flush? Because we're clearing the pixels. That's why we call it flush. So we're clearing the pixels in here, and let's also expose this. I'll define this rather. So we're clearing the pixels, and then we're doing all of the drawing in here. Now obviously we still have to initialize all of all of this data. So yeah, let's do that. And we can do that in the constructor. So what we'll do is we'll create this shader program first, and let's add a private function for that called let's call it create shader program. And what we'll do in there is simple. It's like we'll basically just compile the vertex shader and the fragment shader, and then we'll link that to the program, and that's it. Now, to create the vertex and fragment shader, we'll also have to compile the shaders. So let's create this compile shader function that basically takes an enum for the type of shader it compiles, and also a const char pointer for the source code of that shader program. And yeah, let's define our shader programs above here. So let's create a static const char pointer fragment shader, and this will be a raw string. I think, oh, how was it? We do it like this, yeah, and like this, and now you can add any code you like in here. Now, for the fragment shader, it will be fairly easy. We'll just add the 460 core for our version, and we'll define a autoback for frag color, and in our void name, I guess, in there we'll just set frag color to be a vec4, and all of that will be white. So we can just set that to 1.0. Now the next thing we'll have to define is the vertex shader, and we'll set it up so that we'll just pass in the vec2 for the position, and this will be at the location 0 for the attribute pointer. And another thing we'll need is the viewport size, right? Since we are trying to render this with any size of window. And so what the fragment shader, the vertex shader will try to achieve is that the position is normalized and centered in a way. And yeah, to do that we'll have to calculate the centered position, and because we're like, if I was, I'll draw it for you. So basically, if you have this pixel, the position of the pixel would be here, but you're trying to center it, so you have to like offset it to here. You have to, like, this is just a vector of 0.5, 0.5. Right, so that's why we'll do that first, and then we have to normalize the position, and we can do that by normalize I mean that the position is adjusted to the viewport size, and we'll do that by just dividing the centered position with the viewport size. And lastly, we have to clip the position. I don't want, like, I don't like the default OpenGL coordinate system, the NDC, that they provide. So like, I want it to be so that 0, 0 is up here, and that isn't the case like with default OpenGL, right? So we'll have to take a few adjustments by first multiplying the x by 2, and subtracting 1. And the other one will be subtracting the normalized position dot y times 2 and removing 1. And if we do that, we can actually apply the GL position to that, and that is a gag 4. So we'll have to put in the clip position and 0.0 for the Z because it has no depth, and yeah, that should be it. Okay, now, well, when we compile the shader, what we have to do is we'll need to do it like this. Like, we'll have a GL event, the vertex shader, and that will be the compiled shader program of GL vertex shader, right? And putting in our vertex shader source. Yeah, and this needs to return GL event. And same goes for the fragment shader. Now, after doing that, well, what will we do? We'll have to initialize the actual shader program, and we can do that by first calling the GL create program, and after that we can attach the shaders, so the vertex shader and fragment shader, to the actual created shader. And yeah, after that we can delete those. And calling, when we're talking about delete, it would probably also be useful if we didn't leave leaks. So let's call glfw terminate and glfw destroy window, and also let's create a destructor for this. So that's in there. We'll check, do we have a shader program? If so, we'll delete that program. If we have a vertex array, we'll delete the vertex array. 1, and we'll pass in a vertex array. And lastly, we'll do the same for the vertex buffer by calling gl delete buffers. 1. And vertex buffer. Okay. Now that we've done that, we can also delete the vertex shader and the fragment shader since we attached it, so we don't need it anymore. Now we also have to define this compile shader stuff, and we can do that by creating this shader first, and it will just be a call to gl create shader with the type passed in, and this now the source will be provided later with this GL shader source. We'll give the get source and now pointer for that. Oh damn, no. Okay. And then we just compile the shader. And yeah, that's it for the compile shader call. Now note that we don't have any error handling in here. This has no error handling, and that is intentional. So we'll create the shader program. Oh, not like that. Shader program. And after we've created the shader program, well, we're always passing this viewport size, right? So we'll also have to like get the location of that. So we'll have to create a GL int for the vertex, or no, how do we call it? Uniform viewport size location, and we'll initialize that up here. Uniform viewport size location, and that'll just be GL get uniform location, and the name is, how do we call it, viewport size, and of our shared program. Or did we set the reversed order? Yeah, obviously it is. And yeah, now we're pretty much done with our shader stuff, and we can actually get to full and define the arrays and buffers. So we'll call vertex buffer, and let me reopen this because my LSP was, I feel like it was kind of lagging. So let's generate these buffers and also bind the vertex array first, and then bind the buffer, so the vertex buffer to GL array buffer, so that it remembers that, and pass that buffer. And now we can define this vertex attrib array. So this 0, it has two components, both of them are floats. This won't be normalized, and the size of them is the size of a glm vec2, since we're storing them as glm vec2s. And what else does this taken? The size, the type. What? Yeah, what else? Yeah, the stride, right? Oh no. Too many arguments. Oh, GL enable. We have to do it like this: GL enable and vertex array attrib, or vertex attrib pointer, right? GL vertex attrib pointer. Yeah, there we go. 0. So this is the first one. 2 elements, float, false. Size of a vec2, and lastly 0 for the stride, and cast that to a void pointer to be unsafe. And yeah, that's pretty much it. We can unbind the buffers. This is nitpicking, but yeah, I like to be clean, right guys? That's also why I'm programming everything into a single file. Now that we've done that, we have all the initialization stuff done, and we can actually start rendering things, which is pretty fortunate. And the way we'll do it is simple. Well, let's check if we even have anything to render. If it's empty, we'll just return immediately. There's no point setting anything up, right? Otherwise, we can start doing stuff. I guess. Well, we'll create an array of GL ints, for to be specific, for the viewport. So remember how we called GL viewport in here and set those 4 fields? Well, we can also retrieve them back, since OpenGL used like this global, this global model. So you can just call GL get integer gl get integer value. Yeah, and then you can just get the viewport, and now you have to give a pointer to fill, so we'll give the data, and now we have that viewport, and at fields at indices 2 and 3 we have the width and height, so we can set these in here later. So what we'll do is we call GL use program for our shader program, and we'll set our uniform to floats, and those will be the location of that. And let's pass these in here, so pass in the float for the viewport at index 2 for the width, and do the same in here for viewport at the index of 3. Then bind the vertex array, and vertex array, bind the vertex buffer, GL array buffer slot to be that, GL bind vertex buffer, GL array buffer, too few arguments, bind vertex, no, we only want to bind a buffer. And now we can actually fill the data. So you know how I was talking about that we have to inject all of these pixels into the buffer, and since we are using a stat vector, we can just call it like this, such that, like, how can I say it, like, you have that, and you can just take the size of, well, the second argument is how many bytes we're going to be putting in, right? So you can say mpixels.size is the amount of bytes, or the amount of elements, and the amount of bytes will then be the size of a gln vec2, since that is all that is being stored, times that size. And next we'll give the data, so the actual like starting point, and lastly we'll set that to dynamic draw, since we'll be resetting that frequently. And let's then call GL draw arrays, and we'll use GL points, not GL triangles. You might use GL triangles a lot, but you won't have to do that in here. How many points is that? And yeah, that's it. Now we can bind the buffer back to 0, also the array buffer. We'll bind the vertex array to 0, and we'll use no program anymore. And yeah, that already looks quite nice. So let's check and see if this even compiles properly. No, it doesn't. Why is that? Oh, no. Wait. Source main.cpp in the line 121 here. Since we're not returning the shader. And now, yeah, obviously this will cause problems if we have only 4 declared it but not defined it. So let's just do this one now. Okay, now it runs. And nice, it runs without a problem, which is very fortunate. And now we want to make sure that it does actually render stuff. So let's go ahead and fill the pixel manager, right? So do the same for y, and pixel manager.add pixel x y. Now if we only call that in here, it would only do that one frame, since we're flushing that always, and then it would never add them again, so I have to do that every frame. And then we can see if it works. And it doesn't seem to work for some reason. Well, it might be because of the order of things. So we're clearing the color off of it, flushing that. Let me check. I found the bug. It was the fact that in here we're passing on vertex shader twice, even though that is a fragment shader. So let's try to rebuild it. Oh, it still doesn't work. Damn, okay. Let me continue checking. Okay, I guess we also have to link the program. But I sort of have everything. See, that's why you add error handling. Like, I didn't add error handling in here, right? Because I was lazy. But you should, like, if you're actually trying to build this out and work with it properly, like, you should definitely add error handling. So yeah, but yeah, even though I linked the program, it still doesn't seem to work. So yeah, let me continue checking. Okay, there were a lot of problems. So I guess in the shader code, like, I didn't really differentiate between fragment and vertex shader, and yeah, I also had a syntax error here because I didn't add a semicolon. And another thing I did is make the raw string like completely wrong. So like you don't declare a raw string like this, but rather you do it like this. Yeah. Now, after knowing that and doing this, it might work now. Oh, and yeah, it does. Okay, so now what we've done is we've added an API to add pixels to a screen. Now, there's one final thing I'd like to do. It is to add some kind of unit size, because you've seen how each pixel isn't like necessarily like one pixel in size, but rather it could be bigger. So let's do it like this, where the y's and x's is multiplied by the unit size, and let's also keep the actual naming conventions in place, and yeah, let's set the unit size to, I don't know, 5 for example. And if we do that and compile that and also run that, you see how it stretches, meaning that it does apply the offset properly. However, you should also set the GL point size. So set that to the unit size. Now you should see a way bigger pixel. So if we were to do only add 1 pixel at 10, it should still be noticeable. Yeah. And now finally we can actually get to the actual logic of the game of life. Now what we have to do is program all of this. So what I'd like to do is I'd like to have a unordered set of positions for the, let's say, entities instead of pixels, and this fails to be created because there's no vector2 hash, so we'll have to define our own vector2 hash. And to be honest, I don't know that off the top of my head, but I prepared one right here. So yeah, this is just a hashing function for the vector2 for the unordered set to use. So yeah. Now for the injection part, we'll just go through each pixel, or yeah, entity rather, and call manager.add pixel at entity.x and entity.y. But the more interesting part is the update. Now let's add a delta time and also a m update counter, so, or m updater, or how's it called? M update time. Let's set it to 1 so that only every 1 second this updates. And let's do it like this. We'll have an accumulator, and the accumulator plus equals delta time. And if the accumulator is bigger than the update time, or if it's smaller or equal to that, we'll just return. Otherwise the accumulator will be 0, and then we can actually update. Let's also add the logic for delta time in here. So we'll have a last frame time in here. This is just GFW get time. This is the double, so we have to cast that into a float. And let's also just put the delta time in here. And let's say the current frame time is, yeah, the same as we did in here. And the delta time is the current frame time minus the last frame time. And the last frame time is the current frame time. And yeah, that's it. And yeah, that's pretty much it, isn't it? Yeah, I guess. Yeah. Yeah. So what we can do now is we can call game of life update and pass in the delta time, and let's just ensure that this works properly by saying 1 second past in here. One second passed, 1 second passed, 1 second passed, so this works. And now we actually have to update stuff, right? So now, I guess now is a good time to go over the rules of the game of life. So we have the rule that any live cell with more than 3 neighbors dies. This is overpopulation. And any live cell with less than 2 neighbors dies as well. So this is underpopulation. So only cells or entities with 2 or 3 neighbors survive. And now the third one for creation is any dead cell with 3 neighbors awakes. And yeah, with that we can start creating the logic. So what we'll have to do is we'll store the current generation that we have, and we'll create the next generation based off this current generation. So the next generation will have to be stored in the entities, right? So let's create that in here. Entity and current generation for each entity in the current generation. And now we need some kind of function called get neighbor count, which calculates how many neighbors an entity has. Get neighbor count, and in there we'll pass in the IVEC2. So this will return a size t. Let's call it get neighbor count, and let's pass in gln-vec2 for the entity. And what we'll do in here is we'll call we'll go ahead and say, okay, we'll have an integer I starting at -1. I is less or equal to 1, and I plus plus. And or X is a more intuitive name, and we'll do that for Y as well. So that we, like, if we have a grid like this, and this is the entity, will go through each cell, so each neighbor. So if X equals 0 and Y equals 0, we're at the entity itself, so the delta, so we'll just continue. Otherwise, we'll check. So we want to return a neighbor count, right? So we'll set that to 0 and return that in here. Return the neighbor count. But what we'll do in here is we'll say, okay, if the entities that contains such an entity minus the delta, so minus this gln-vec2 x, y, if it contains that, then the neighbor count increments by 1. And with that we get the neighbor count, and now what we can do is we can check, okay, if the neighbor count is equal to 2 or the neighbor count is equal to 3, then the new generation also has this entity. But if there is more than 3 or less than 2, so 1, 0 or 4, 5, 6, 7, 8, 9, no, 8 is the max, then it will die. Now, well, okay, a problem that we still have is that we will have to pass in the current generation, right? Because the new set is empty if we do that. So let's extract that into a using statement using entities like this, and then we'll just do entities and do entities const, and let's say entities are generation, and let's call this generation as well, life generation, game of life generation. Okay, and let's not use the entities but rather the generation. So in here we'll have to pass in our current generation. So the neighbor count, if it's 2 or 3, we'll insert it. Okay, so with that we have these two rules added already. However, this rule still has to be added or implemented rather. So what we'll do is any dead cell with 3 neighbors awakes. What can we do for that? Yeah, so what we'll have to do is we'll have to keep a track of all of the dead neighbors. Okay, so well, you need a position and an amount, right, and still this vec2 hash, and this will tell you, okay, how many dead neighbors do you have. Like each entry is a dead neighbor, and it'll tell you how many dead neighbors, like how many neighbors that neighbor has. So now instead of doing it like this, we'll create a new function called returning a vector of glm vec2s, and it's called get all possible directions, like from your own. And all you'll do in here is the exact same what we did in here, and we'll create this and call directions, and dirs dot and place back xy, and we return these dirs. And instead of doing this with the for loop, we can reuse that logic, saying for const dir in get all neighbors directions, const order reference dir and get all neighbor directions, and we'll pass in, we'll have to pass in the entity minus that direction instead of just that. And yeah, that'll do. And also now, if we add this, we'll just say, okay, we get a dir and get all possible directions, and if the current generation doesn't contain this possible neighbor, and the possible neighbor is entity minus direction, then the dead neighbors count at that possible neighbor, well, it increments, right? So we'll do it like this. this seems to doing fine. And now we have something that tells us how many dead neighbors we have, and now we can iterate over that again, where we get the position of the dead neighbor and the neighbor count in all of the dead neighbors. And if the neighbor count is equal to 3, then we'll insert that as well, so this new position as a new field. So with that we have the third rule implemented, and if I've done everything right, this should work. Now the reason nothing's happening right now is because well, this is initially empty, the game of life, right? So what we'll have to do is we'll have to initialize this. So let's do that by doing 100 or yeah, 100 entities. So we'll create 100 entities. This is the generator, and we'll need a uniform int distribution for the for the range, and let's set the range to be from 0 to 200, or let's say 700, and n entities will in place the generate or the range of that generator, and we'll do that twice. Now nothing happened. If we do it like this, so densely. Let's make it like this, 40. Let's say 0 to 40, and let's also make the unit size not as big. 1.0f. Wait, 1.0f will be unimaginably small. But yeah, it seems to be working. So let's make this 5.0. And yeah, you can see here that it's kind of working. So yeah, let's increase the amount of things we're adding, and let's also double the size of the thing here. And yeah, you can see this starts to look very cool. Yeah. We've implemented the game of life, guys. Let's take a look at this. Yeah, we should probably increase the size of oh damn, take a look at this. Okay. Let's try to make the tick speed a bit faster. So the update time, let's set it to 0.05f. So we have 20 generations in a second. See that? That looks very nice, guys. Yeah, that's very cool looking. Yeah. We've implemented the game of life. Nice. That's so cool. Let's try to make it as fast as possible. Just 2 stress tests. you can see this seems to be working very well. Nice. Okay, very cool project. I hope you learned a lot, and if you've learned something from this video, leave a subscribe, and yeah, goodbye guys.